objectives. Visual interpretation of remote sensing images is one of the most powerful ways to retrieve information. Depending on the quality of image and human expertise in image interpretation, many of the attributes are readily identified by human eyes. However, at times it is required to highlight or enhance certain features of interest in image to make the image better interpretable. This is achieved by techniques known as image enhancement and transformation techniques required to increase the quality of remote sensing data. For this purpose, we have digital image processing which improve the quality of the image. In this chapter, we will discuss about image processing stages, pre-processing, image enhancement, image classification, supervised and unsupervised, image transformation, advantages of image processing, components of image processing system. Image processing. The remote sensing data can be analyzed using the visual image interpretation techniques if the data are in the hard copy or pictorial form. It is used extensively to locate specific features and conditions which are then geocoded for inclusion in GIS. Visual image interpretation techniques have certain disadvantages and may require extensive training and are labor intensive. In this technique, the spectral characteristics are not always fully evaluated because of the limited ability of the eye to discern tonal values and analyze the spectral changes. If the data are in the digital mode, the remote sensing data can be analyzed using the digital image processing techniques, and such a database can be used in a raster GIS. In application where the spectral patterns are more informative, it is preferable to analyze digital data rather than pictorial data. In today's world of advanced technology where most of the remote sensing data are recorded in digital format, virtually all image interpretation and analysis involves some element of digital processing. Digital image processing may involve numerous procedures including formatting and correcting of the data, digital enhancement to facilitate better visual interpretation, or even automated classification of target and features entirely by the computer. In order to process remote sensing imagery digitally, the data must be recorded and available in a digital form suitable for storage on a computer compatible tape or disk. Obviously, the other requirement for the digital image processing is a computer system, sometimes referred to as image analysis system, with the appropriate hardware and software to process the data. Several commercially available software systems have been developed specifically for remote sensing image processing and analysis. Image proceedings can be done in the categories pre-processing, image enhancement, image transformation. Pre-processing. Pre-processing functions involve those operations that are normally required prior to the main data analysis and extraction of information and are generally grouped as radiometric or geometric corrections. Radiometric corrections include correcting the data for sensor irregularities and unwanted sensor or atmospheric noise and converting the data so they are accurately represented the reflected or emitted radiation measured by the sensor. Geometric correction includes correcting for geometric distortion due to sensor earth geometry variations and conversion of the data to real world coordinates, that is latitude and longitude on the earth surface. The objective of the second group of image processing functions grouped under the term of image enhancement is solely to improve the appearance of the imagery to assist in the visual interpretation and analysis. Example of enhancement functions include contrast stretching to increase the tonal distinction between various features on the scene and spectral filtering to enhance the specific spatial pattern in an image. Image transformations are operations similar in the concept of those for image enhancement. However, unlike image enhancement, operations which are normally applied only to a single channel of the data at a time. Image transformations usually involved combined processing of data from multispectral bands. Arithmetic operation, that is subtraction, addition, multiplication, division, are performed to combine and transform the original band into new images which better display or highlight certain features on the scene. Some of the operations include various methods of spectral or band rotating and a procedure called principal components analysis, which is used to more efficiently represent the information. Image classification and analysis operation are used to digitally identify and classify pixels in the data. Classification is usually performed on multi-channel data sets, and this process assigns each pixel in an image to a particular class or theme based on statistical characteristics of the pixel brightness value. There are a variety of approaches taken to perform digital classification. Preprocessing operations, sometimes referred to as image restoration and rectification, are intended to correct for sensor and platform specific radiometric and geometric distortion of data. Radiometric corrections may be necessary due to variation in scene illumination and viewing geometric, atmospheric condition and sensor noise and response. Each of these will vary depending on a specific sensor and platform used to acquire the data and conditions during data acquisition. Also, it may be desirable to convert and calibrate the data to known absolute radiation or reflectance of units to facilitate comparison between data. Image enhancement techniques. Low sensitivity of the detectors, weak signal of the objects present on the Earth's surface, similar reflectance of different objects and environment condition at the time of recording are the major causes of low contrast of the image. Another problem that complicates photographic display of digital image is that the human eye is poor at discriminating the slight radiometric or spectral differences that may characterize the features. The main aim of digital enhancement is to amplify these slight differences for better clarity of the image seen. This means digital enhancement increases the separability or contrast between the interested classes or features. The digital image enhancement may be defined as some mathematical operation that are to be applied to digital remote sensing input data to improve the visual appearance of the image for better interpretability or subsequent digital analysis. Since the image quality is a subjective measure varying from person to person, there is no simple rule which may produce a single best result. Normally, two or more operations on the input image may suffice to fulfill the desire of the analyst. Although the enhanced product may have a fraction of a total information stored in the original image. There are a number of general categories of enhancement techniques. As in many outer areas of knowledge, the distinction between one type of analysis and another is a matter of personal taste and need of the interpreter. In remote sensing literature, many digital enhancement algorithms are available. They are contrast stretching enhancement, ratioing, linear combinations, principal component analysis, and spatial filtering. Broadly, the enhancement techniques are categorized as point operation and local operation. Point operation modify the value of each pixel in an image data set independently, whereas local operation modify the values of each pixel in the context of the pixel values surrounding it. Point operation include contrast enhancement and band combinations, but the spatial filtering is an example of local operation. In this contrast enhancement, linear contrast stretch, histogram, equalization, logarithmic contrast enhancement and exponential contrast enhancement are considered. Image classification. Image classification is a procedure to automatically categorize all pixels in an image of a terrain into land cover classes. Normally, a multispectral data are used to perform the classification of the spectral pattern present within a data. For each pixel is used as a numerical basis for categorization. This concept is dealt under a broad subject, namely pattern recognition. Spectral pattern recognition refers to a family of classification procedures that utilize this pixel by pixel spectral information as the basis for automated land cover classification. Spectral pattern recognition involves the categorization of image pixels on the basis of the spatial relationship with pixels surrounding them. Image classification techniques are grouped into two types, namely supervised and unsupervised. The classification process may also include features such as land surface elevation and the soil type that are not derived from the image. A pattern is thus a set of measurements on the chosen feature for the individual to be classified. The classification process may therefore be considered a form of pattern recognition, that is, the identification of the pattern associated with each pixel position in an image in terms of the characteristics of the object or on the earth surface. Supervised classification. A supervised classification algorithm requires a training sample for each class, that is, a collection of data points known to have common from the class of interest. The classification is thus based on how close a point is to be classified is to each training sample. We shall not attempt to define the word close other than to say that both geometric and statistical distance measures are used in practical pattern recognition algorithms. The training samples are representative of the known classes of interest to the analyst. Classification methods that rely on the use of training patterns are called supervised classification methods. The three basic steps involved in a typical supervised classification procedures are: training stage. The analyst identifies representative training areas and develops numerically descriptions of the spectral signature of each land cover type of interest in the scene. The classification stage. Each pixel in the image data set is categorized into land cover class it mostly closely resembles. If the pixel is insufficiently similar to any training data set, it is usually labeled unknown. The output stage. The results may be used in the number of different ways. Three typical forms of output products are thematic maps, tables, and digital data files, which become input for GIS. The output of image classification becomes input for GIS for spatial analysis of the terrain. Unsupervised classification. Unsupervised classification algorithms do not compare points to be classified with training data. Rather, unsupervised algorithms examine a large number of unknown data vectors and divide them into classes based on properties inherent to data themselves. The classes that result stem from differences observed in the data. In particular, use is made of the notion that data vectors within a class should be in some sense mutually close together in the measurement space, whereas data vectors in different classes should be comparatively well separated. If the component of the data vector represent the responses in the different spectral bands, the resulting classes might be referred to as spectral class as opposed to information classes, which represent the ground cover type of the interest to the analyst. The two types of classes described are information classes and spectral classes, may not exactly correspond to each other. For instance, two information classes, corn or soya beans, may look alike spectrally. We would say that the two classes are not separable spectrally. At certain times, the growing season of corn and soya bean are not spectrally distinct, while the other at times they are. On the other hand, a single information class may be composed of two spectral classes. Differences in planting dates or seed variety might result in the information class corn being reflected in differences of tasseled or untasseled corn. To be useful, a class must be informational value and be separable from other classes in the data. Image transformation. Image transformation involves manipulation of multiple bands of data from a single multispectral image or two to more images of the same area acquired at different times. In this process, a raw image or several set of images undergo some mathematical treatment to achieve a new imagery. As a consequence, a new resultant transformed image generated from two or more sources highlights particular feature or properties of interest better than original input image. Hence, the transformed image may have properties that make it more suited to a particular purpose than original input images. Image transformation techniques are useful for compressing bands having similar kind of information into fewer bands and also to extract new bands of data that are more interpretable to a human eye. There are two kinds of image transformation techniques: arithmetic operation and image fusion. Arithmetic operation is one of the techniques of image transformation is to apply simple arithmetic or logical operation to the image data. Arithmetic operation of addition, subtraction, multiplication and division can be performed on two or more images of the same geographical area. The prerequisite for the operation is that all input images should be co-registered. These input images may either be individual bands from image acquired at different dates or separate images bands from a single multispectral image. Image fusion is a process of combining relevant information of two or more remotely sensed images of a scene into a highly informative single image. The primary reason image fusion has gained prominence in remote sensing application is based on the fact that the remote sensing instruments have design or observational constraint. Therefore, a single image is not sufficient for visual or machine level information analysis. In satellite imaging, two types of images are available. The panchromatic images acquired by satellites have higher spatial resolution and multispectral data have coarser spatial resolution. These two image types are merged or fused in order to get information of both the images in one single image. The image fusion techniques thus allows integration in different information sources, and fused images can have complementary spatial and spectral resolution characteristics. In other words, fused image will have spatial information of the panchromatic image and spectral information of the multispectral image. Advantages of digital image processing. There are certain thresholds beyond which human interpreter cannot detect minor differences in image feature in an image. For example, if a data is recorded with 256 gray shades, there may be more subtle information present in the image than we can extract visually. Similarly, it becomes difficult to keep track of a great amount of detailed quantitative information such as the spectral characteristics for crop identification proposes throughout a growing season. However, computer is much more adept at storing and manipulating such information. Advantages of handling remote sensing data in digital mode as compared to photographic mode are: ease in the data storage and distribution. Images can be identically duplicated during reproduction and distribution without any change or loss of information. Visualization of greater details. Images can be processed to generate new images without altering the original image. Faster extraction of quantitative information and repeatability of results. Computer-assisted image interpretation approach mimics the visual image interpretation approach to a certain level. Manual image analysis uses most of the elements of the image interpretation such as tone, color, size, shape, texture, pattern, height, shadow, sight and association, whereas computer-assisted image interpretation involves the use of only few of the basic elements of image interpretation. In fact, majority of the all digital image analysis appears to be dependent primarily on just the tone or the color of the image feature, but both manual and digital analysis of remotely sensed data seeks to detect and identify important phenomena in the scene as both the interpretation approaches have the same general goals. Component of the image processing system. The components of the image processing system differs depending on different type of image. For example, satellite images and X-ray images following components are the minimum requirement of an image processing system. Processing device. It may be a general purpose computer according to the task to be performed. The basic use of this device is that it will perform all digital image processing tasks offline. Storage device. Storage devices are used to storing of images for different purposes and uses. Display device. It is used to displaying data. Example of a display device is generally a color monitor. Image processing software. Image processing software such as EGRIS, ERDAS, NV and Geomatrica are specifically designed programming modules that perform specific tasks. Printing device. It is used for representing and storing image data in hard copy format. It could be a laser, inkjet or any other printer. It is important to note that the factors should be considered while selecting a digital image processing system. Number of analysts and the mode of operation. You should consider a software which could be accessed and interactively used for data processing by at least a number of people involved in the study. Memory and processing specification of the computer. Processing of different types of digital remote sensing data require different processing capabilities and memory usage. You should choose a software that is compatible with the specification of the computer. You have to buy a computer with minimum specification that is required to process the data of your interest. Operating system. The operating system must be powerful and easy to use. DOS, Unix and Windows are the most universally used operating system. The chosen image processing software should be compatible with the operating system in your computer. Storage. Digital images are stored usually in matrix form with various multispectral bands and in different formats. Softwares which are capable of storing and processing the concerned image format should be considered. Display resolution. Different image types require different display resolution. Hence, you should consider software which is capable of displaying highest resolution. Preprocessing functions involves those operations that are normally required prior to the main data analysis and extraction of information and are generally grouped as radiometric or geometric corrections. Image enhancement and transformation techniques are very useful in remote sensing because they make remotely acquired data more visible and usable. Data acquired may not always of highest quality due to technological or other atmospheric interferences, and rectification techniques remove these disadvantages. While most of these techniques enhance data quality and have wide variety of applications, some of them may result in spatial or spectral distortion or mask certain information while highlighting others. Image classification techniques are grouped into two types, namely supervised and unsupervised. Image transformation techniques are useful for compressing bands having similar kind of information into fewer bands and also to extract new bands of data that are more interpretable to human eye.